So now that we have this quantity called an object's momentum, which is its mass times its velocity, what do Newton's laws look like if you're thinking in terms of momentum? So Newton's first law says, you know, in my own kind of simplified viewpoint, it says that if there's no net force on an object, the object will move at constant velocity, both magnitude and direction, constant velocity. How does that look in the world of momentum? And the first law really doesn't change a lot. The first law is basically that if there's no net force, it means constant momentum. And that's constant magnitude and direction of momentum. So we get basically the same thing because, you know, the momentum points in the same direction as the object's velocity. The only difference is you multiply by the mass. As long as the mass isn't changing during a process, then this doesn't really make any difference one interpretation versus the other one. And we're not going to try to handle cases where the object's mass changes in the middle of the problem. Leave that for another course. The second law is a lot more interesting. We mentioned in the last video that the second law in this new viewpoint is that the force on average is equal to delta P over delta T. That's what F equals ma becomes in this viewpoint. Or another way that people often write it is that delta P equals F on average times delta T, which of course is the same equation, but people often act like this is a revelation that you can multiply both sides by delta T. I don't quite know why that is the case. But anyways, this version of Newton's second law here is often referred to as impulse momentum theorem. And the reason why it's called impulse momentum theorem is because the quantity F delta T, or F on average delta T, I have to be a little bit sloppy with these averages because we can't use calculus in this course, is equal to capital J on average. And J is referred to as the object's impulse, or the impulse on an object. So if you see anything referring to the impulse acting on an object, that just means to take the force on an object and basically multiply it by delta T. As long as the force is constant, that works. So what impulse momentum theorem says is that if you know the impulse on an object, then that's just simply equal to the momentum on an object. So, you know, sometimes people will write impulse momentum theorem as J equals delta P, done. And physicists like these really short, compact equations. But this is really where the action is. That's really what it means. It's just Newton's second law reinterpreted in terms of momentum and this other quantity called impulse. This form, the impulse momentum theorem, is useful in cases where a lot of real life cases where you kind of know something about the force acting on the object, but you also know maybe how long the force is acting on the object. Because, for instance, well, maybe I'll save this for another video to explain a little bit of how you can use impulse momentum theorem to solve some problems and, or more importantly, think about some problems conceptually and make them a little bit easier to understand than they would be with our old viewpoint of Newton's laws.